Welcome everyone. As I told you that catalysis is very important, and here in this lecture I will talk about little bit of research related things, but very important for catalysis. I will talk about surfactant, I will tell about the micelles and reverse micelles, then how the catalysis can happen in micellar micelle within the micelle. Then I will tell about the admicelle and how admicelle can act as a can hold the catalyst and can act the catalysis in a favorable way. And then I will tell about the nanoparticles. Nowadays very important field of research, you know, that nanocatalyst. So, I will cover all those things in this lecture. Now, what is surfactant? You know, surfactant is a very common thing. We every day we use the surfactant in detergents, in toothpaste, and the speciality about that surfactant is that it has a very special chemical structure. And this surfactant, why it is called surfactant? Because it is a surface active agent. So, the whole term is surface active agent, which is called in abbreviated way, this is surfactant. Okay. So, what surface active agent means what? It is reducing the surface tension of water. Surfactant can reduce the surface tension of water. Now, what is the speciality about the surfactant in relation to the chemical structure? The chemical structure is shown here. For the surfactant, you can see here there is long chain, carbon chain here. There may be 15 carbon or 18 carbon like this. So, it is a long chain, but you can see the two ends. What are the two ends? In the this end you see it is carbon end. It is carbon end, so it is hydrophobic end. Okay. It is also called tail, hydrophobic tail. Okay. And the other end you see it is the this is written as G. So, what is G? G is some ionic end. Okay. It may be NH3 or NR3 or it may be means CO minus, or it can be SO3 minus. So, this is the ionic, this is called head. So, it is ionic head. Now, so this is the structure. Now, if we represent this as this one, so this is the head and this is the tail. So, the surfactant molecules, if you put in water in a small concentration, then it will be acting as an electrolyte. Okay. So, it will form some start forming some layer in the interface of water and air. But if you increase the concentration and if you reach the CMC means critical micelle concentration in water. So, for example, I am talking about water, then what will happen? These surfactant molecules will arrange themselves in some spherical structure. Okay. This is shown in 2 dimension, but actually it is 3 dimensional structure, it is a spherical structure. So, what is this is called micelle. So, it happens only above the critical micelle concentration. Now, what is the speciality about it? This is dynamic, means it is forming and breaking like this, but it has a in this structure you can see here all the carbon ends are here inside the center, it is the core, it is called hydrophobic core, and all the hydrophilic groups, end groups, that means this group are exposed towards the water. This is a water medium. Okay. In water it is present like this. Okay. Now, here the picture is shown in a bigger way. So, inside it is the hydrophobic core. Now, some hydrophobic molecules, say for example, benzene or chloroform, those types of molecules, they are not soluble in water, right. So, if you put a little amount of this type of molecule in water, then they will form emulsion. So, they are not dissolved in water. Now, they can be dissolved in this core, in this hydrophobic core, but solubilized. This is called solubilization. Okay. But if you add too much, then it will not be soluble, but if it is less amount, then it can be solubilized here. Now, this in this core some reaction can occur. This is called micellar core. So, micellar catalysis can happen here. So, for example, there are X and Y, can react to form the Z. Okay. So, this can happen here in the micellar core. This is called micellar catalysis. Now, entropy factor, you may tell that this is a little bit away from this catalysis, but you may tell that why the micelles are formed, because once we know that natural process, in the natural process always entropy increases, but here when the micelle is formed entropy should decrease, but this is opposite to our concept. How to explain this? Because this is you have to think about the whole system. Okay? When the micelles are formed, so water structure is breaking, and this so their entropy is increased. Okay? Now, if you think about the total system, maybe in this case entropy is decreased, but in the water entropy is increased. So, as a total you have to think, and as a total entropy is increased. So, this is not catalysis related, but just I wanted to mention. Now, this is very very interesting topic, and many reactions that will not happen in homogeneous water or any solvent, they can happen here in the micelle. Okay. Now, this is water medium, but say for example, similar micelle, similar surfactant molecules, if you put it in organic solvent, but containing little amount of water, then what will happen? It is just the reverse, there it is the organic solvent, but little amount of water is present. Then the reverse micelle will be formed. This is the reverse micelle. You can see here that that the head groups, because little amount of water is there, so that will be inside the core. Okay? And then these head groups, you see it is facing towards the water, and this is the organic solvent. So, carbon ends because they are hydrophobic, so it will remain towards the organic solvent, because we know hydrophobic things like hydrophobic things. So, organic solvent is hydrophobic. So, like chloroform, hexane, all those things. So, it will form like this. This is called reverse micelle. Okay. Here also some reaction is possible. Say A plus B gives C. So, this type of reaction can happen here in the reverse micellar core. Okay. This is also very interesting. Okay. Very interesting. Now, as I told you that catalysis, when it is heterogeneous catalysis, then it is easy to separate, the catalyst is easier to separate. Now, considering the similar concept as we have seen in the micelle, so micelle, how can you separate? So, once the reaction is happening, how can you separate the product? How can you separate the micelle or surfactant? That is very difficult, na? So, here you can see we can have the similar concept, but we can do it on solid surface. Then the solid is easier to remove by filtration or something like that, or settling. So, you can see here similar type of thing happening, but it is happening on the solid surface. On the micelle it is happening, but micelle is adsorbed on the solid surface. This type of micelle, it is not spherical micelle, but it is adsorbed on the solid surface. That is why it is called admicelle. Admicelle means adsorbed micelle. Okay. So, here you can see that this type of the hydrophilic end of the micelle of the surfactant is facing toward the solid surface. This is the surface alumina. Okay. So, alumina alumina depending on the pH ZPC. What is pH ZPC? pH ZPC is some characteristic for a solid surface. Say for example, it is a pH actually. So, on at pH ZPC some solid surface is neutral, means charge is 0. Okay. But if you change the pH ZPC, that means the pH, the solution pH, if you make it lower, means if you go to lower pH, then it will become positively charged, the surface will be positively charged. If you go to higher value, pH higher value, then the solid surface will be negatively charged. Okay. In case of alumina, the pH ZPC is 9.1. So, if you make the solution pH below 9.1, say for example 4 or 5, then alumina will be positively charged. And in that case, you know, the negative surfactant, it is the sodium dodecyl sulphate SDS, which is represented like this. So, its head group is negatively charged, okay, sulphate group, okay, negatively charged. So, in that case, if the solid surface is positively charged, then it will arrange themselves. The first layer will be like this, then second layer of surfactant will be like this. Okay. So, basically it is Micelle type structure, but it is adsorbed on solid surface. And because why the SMA it is written, because alumina it is modified with SDS, that is why or surfactant, that is why it is called surfactant modified alumina, SMA, surfactant modified alumina. So, this is nothing but SMA. Okay. How it is formed? Alumina you have taken, you have added SDS in very high concentration, you have made the solution pH around 4.5, much below the pH ZPC of alumina, then SDS is arranging in this fashion, it is a bilayer. Okay. And this range, this portion is hydrophobic, this portion is hydrophobic. So, and this is because this is head group is negatively charged, so this is negatively charged. Okay. This you have to remember. Now, if you put manganese 2 plus here, this is cation, right. So, cation will be adsorbed in the negative head group. Okay. And then, so this is the manganese 2 loaded SMA. So, you have loaded manganese 2 on SMA. Okay. And now, if you put KMnO4, then it is a redox type reaction, Mn 2 plus and Mn the 7 plus, okay, 7 plus and 2 plus. So, 2 plus will go to 4 plus and 7 plus will go to 4 plus. That means, it is a redox type reaction, and so here you see that Mn 2 plus is converted to MnO2, okay, MnO2, this red one is MnO2. So, now you find something, it is actually why I am discussing it, because it is a catalyst. Okay. So, in the catalyst it is also MnO2, MnOX actually we have told, because oxidation state is mixed oxidation state. So, we have written MnOX. So, you have learnt that MnO2 is a very good catalyst for H2O2 decomposition, you have learnt it, right. So, here also we will use it as a catalyst. Now, important thing is that because it is negatively charged, the head group, so it is a dye molecule, methylene blue, it is a dye which is positively charged dye, cationic dye. So, this cationic dye will be adsorbed on this negatively charged head group. So, catalyst is there as well as the dye. So, we will show you how the catalyst can degrade the methylene blue dye here in presence of H2O2. So, basically you are preparing a heterogeneous catalyst with MnO2 or MnOX, and you are trying to degrade the methylene blue by using H2O2. So, up to this it is clear to you, I hope, because you have everything you have learnt in the last lecture. Okay. So, H2O2 you learnt, heterogeneous surface, heterogeneous catalysis you have learnt, and MnO2 you have learnt, everything you have learnt. Just application, now we are applying what you have learnt, we are applying that. Okay. Now, you see up to this you know already that you got some SMA MNOX, this is the catalyst, and this is the dye, that is methylene blue, it is adsorbed there. So, both are together, so catalyst and the substrate is together, okay. It is adsorbed here on the same surface, it is adsorbed. Now, you are putting H2O2 and also light. Light is very good, light is also good catalyst to decompose H2O2, right. You have learnt all this thing also. Now, H2O2 will be decomposed, and here in this case it is not oxygen, but it will be hydroxyl radical. So, this type of degradation is called advanced oxidation process or AOP. Okay. So, OH dot is very powerful oxidizing agent, and that is coming from the H2O2 with some catalyst, it is forming that OH dot. So, when OH dot is produced, that will oxidize the methylene blue, okay, and some degradation products will be formed. Now, after that what will happen? The methylene blue will go out, not the methylene blue, the products will go out. So, now keeping the again free, the catalyst is remaining free, okay, for another molecule again of methylene blue to come and react. Okay. So, this is called modified Fenton type catalyst, because it is, why it is called Fenton? Because Fenton, modified Fenton. Why it is modified Fenton? Because actual Fenton, the classical Fenton reaction is happening with iron 2 plus and H2O2. Okay. Iron 2 plus and H, this is the first it is observed by Fenton, and he did the oxidation of tartaric acid. But after that long time this reaction remained unattended. Finally, again from 1960 this Fenton type of reaction is being used for pollutant degradation. Pollutant like methylene blue is also a pollutant, it is a dye. So, this type of degradation, and this is called advanced oxidation process, where OH dot radical, it is very powerful oxidant, okay. Even much powerful than H2O2, and it is taking taking its role, it is oxidizing oxidant as an oxidant to oxidize the organic pollutant. Now, why it is called Fenton? Because in Fenton it is Fe2 plus and H2O2, but it is modified Fenton, H2O2 is there, but it is another catalyst MnO2, okay, and it is photofenton because you are using the visible light also. Now, this is also very important, there are two types of mechanism that is prescribed for this type of reactions. One is the Langmuir-Hinshelwood mechanism and another is the Ille-Riedel mechanism. So, in this type of heterogeneous catalysis, you know, one there is substrate and reagent, or there are two substrates, you can tell. Once at least one substrate has to be adsorbed on the catalyst surface, okay, at least one. It can be two also, both may be adsorbed also, or one at least should be adsorbed. So, if both are adsorbed, both substrates, say for example, A and B are reacting. So, both A and B are adsorbed on the catalyst surface, then this is called the Langmuir-Hinshelwood mechanism. But if one is adsorbed and another is in the liquid phase or gas phase, so it is not adsorbed, but it is coming from the gas phase or liquid phase and reacting, and then it is going out. So, it is reacting with the other substrate in presence of catalyst and it is going out, then this is the Ille-Riedel mechanism. So, these two types of mechanisms are proposed. Okay. For any catalytic heterogeneous catalysis, these two types of mechanisms, mostly these two types of mechanisms are proposed. Okay. I hope you have understood what are the difference between these two. Anyway, so here, so what we have seen here, that Micelle can be used on adsorbed phase to get the catalysis. MnO2 is a very good catalysis or MnOx is a good catalysis, and this is very easy to separate also the heterogeneous catalysis just by keeping for some time. If you keep for some time, this is settling down, and then you can easily take out the solvent from the upper part. Okay. Solvent means water from the upper part. Okay. And also from the mechanism, you have already I have already discussed about the mechanism. So, once you know to want to know the mechanism, then intermediates or products you have to isolate, then only you can speculate the mechanism. So, here it is observed that there are many products where OH dot is attached. Okay. In the substrate OH dot is attached. So, that means this reaction is going via OH dot generation and attack. Okay. That is that you can speculate, but how the products are identified? This is by mass analysis. Okay. This also is very good tool to tell about the mechanism, because you are not isolating, but you are detecting, actually isolating and detecting the products. Or if you can do the intermediates, then it is also good, because then you can speculate the intermediate steps also. Okay. So, this is also dealing with the mechanism. Now, I am going to another very important topic, that is nanoparticle. Nanoparticle is also being used nowadays enormously as a catalyst. Okay. So, those who are not very much familiar with nanoparticles, I can tell you that particles with 1 to 100 nanometer size, at least in one dimension, okay, are called nanoparticles. Why I told in one dimension? Because if, say for example, something is one wire, you can think about one wire. Okay. The wire, say for example, the diameter of that wire is say 50 nanometer, but the length of the wire may be 1000 nanometer. Okay. Then my question is whether it will be called as nanoparticle or not. Yeah, that is why one dimension is coming. So, because one dimension here, that is the diameter is 50 nanometer, even if the length is much higher, that is 1000 nanometers, it is beyond 1 to 100 nanometer size range, still it will be called a nanoparticle. Okay. Because it is nanowire, it is called nanowire. Now, this is nanometer means 10 to the power minus 9 meter. So, you can understand how small it is. Okay. In recent times, huge number of reports are available where nanoparticles are used as catalyst. Why nanoparticles are so much important as catalyst? Okay. So, that I will tell. So, some applications of nanoparticles as catalyst. Here you can see the adipic acid, an industrially important compound. Adipic acid can be synthesized from cyclohexane by using this cobalt nanoparticle. Okay. The details I have not given, but I can tell you that cobalt nanoparticle is acting as a catalyst in this reaction. That cyclohexane, you know, cyclohexane, if you know benzene, then if you remove the double bonds, then it will be cyclohexane. Okay. It is a cyclic compound, but saturated compound. Okay. So, this can be converted to adipic acid, which is very much important for preparing, you know, that nylon 66, you know, nylon 66 is so much important. So, it can be produced from here, hexamethylene diamine and adipic acid, that condensation reaction, that polymer formation. Now, this is nylon 66 polymer. Now, why nanoparticle is so much important? Because of their small size. Nanoparticles are very interesting properties because of their small size. Okay. Say for example, melting point, and these properties are very different from the properties of the bulk materials. Okay. So, say for example, melting point of gold. The melting point of gold, bulk gold is this one 1064 degree centigrade, but melting point of gold nanoparticles can be even below 23 degree centigrade. So, nanoparticle has very different properties than the bulk. Okay. Another is the color. Gold may have different types of colors when they are nanoparticle. Say for example, it can have purple color, it can have blue color, other different colors. Same is true for silver. Silver nanoparticles may have different colors. So, they have different colors from the bulk metal. Okay. Now, nanoparticles have huge surface area. So, they act as a very good catalyst. You know, I have already told you that adsorption is required. So, when surface area is more, then more number of molecules can be adsorbed. So, surface area is very important for catalysis. That is why nanoparticles are very good catalyst. You can see that many journals, catalysis journals are dedicated for catalysis or catalysts. Very good quality journals, they are dedicated for catalysis. So, you know how important now it is to develop some catalysis or to do some reaction by using some catalyst, good catalyst. Okay. Now, when I am talking about the nanoparticles, you can see here that how the volume surface to volume ratio and the surface area, how it is related. This is 8, volume means cubes, you know, it is small cube, very small, then bigger than this, then bigger than this, then bigger than this. So, how these properties, these 3 properties are changing when you increase the size. Say for example, this is 2 to the power 3, 2 cube and then this is 4, then 6, then 8 like this, then how the surface area, you can calculate it, surface area. So, there are 6 surfaces, surfaces, so you can calculate easily. Then volume is this one, surface area is this one. So, what is the surface to volume ratio? So, you can see that as the size is increasing, then the surface to volume ratio is decreasing. This is very important term for the catalytic property. When surface to volume ratio is high, then catalyst will be better. Okay, it will have better catalytic properties. So, smaller particles are better catalyst, like this one. This is better catalyst than this one. If it is the same material, but size, only size is varying, then this is better catalyst than this one. Okay. Now, shape matters. Shape, it is say triangle shape or rod shape or spherical shape. So, shape also is important, because here the adsorption and here in the surface the adsorption, they may be different. Okay. That is why shape, depending on shape also catalytic property will vary. Now, crystal facets. What is facets? Flat faces of crystal. Such they are recognized 110, 111, etc. So, facets also, there are some catalysis facet dependent. Okay, crystal facet dependent catalysis. So, all these topics are now very important for nano catalysts and very important and upcoming fields. Now, to do this, that MnO2, that MnO2 actually was the size characterized this nano rods type. Okay. That is also nanoparticle that I discussed, that SMA surface, that MnO2, that is nano size, nano rods. So, this is the reference for this, and nanoparticles I have not discussed much. This is more very general thing I discussed. You can get any from anywhere, from any book, nano related book, you can get that. So, I am not giving any reference here. This is very general thing I have discussed, but what I wanted to tell in my last lecture, that very upcoming fields what are there but it is related to kinetics, it is related to catalyst, it is related to homogeneous heterogeneous catalysis. So, it is very related topics, but very upcoming things. Okay. Why it is important? The catalyst is so much important, you can understand by seeing that those examples. Okay. Now, in this last lecture, I have discussed about the catalysis is in confined environment such as within micelle and reverse micelle, and I have also discussed the catalytic properties of nanoparticles that depending on the size and shape and facet also. So, all those things are discussed in this lecture. These are very important topic today. So, thank you very much.